All right, welcome to week 5. We're still sticking with some of the more difficult content, but hopefully this one should be pretty straightforward. We're looking at chemical energies, which is going to be on your page 77. And there's a few things we need to cover, such things like as enthalpy change, so endothermic, exothermic, which I'm very sure you're aware of, and then standard enthalpy change, which is 3 to 4 different types of reactions. We're going to have some rules for this, a little bit like last time, where these are the rules that we play by, and these are the things we can do. We're going to try and frame it in that context. So there are a few things that we need to know. First of all, with enthalpy change, whenever we mention enthalpy change, we're saying is the heat energy transferred in a reaction at a constant pressure. So if I react something in a beaker, where does that energy go? Is it being taken in? Is it being released out? What's actually happening with that energy? So the energy change is an enthalpy change. Some of you might be thinking, why don't we just call it energy change? But enthalpy takes into account the amount of stuff. That's the difference. The units then to take into account stuff is kilojoules, that's energy. Per mole is per amount of stuff. Standard states. Whenever we mention the term standard states, we're saying these are the states that it would exist under standard conditions. And standard conditions are 100 kPa and 298 Kelvin. That's basically normal room conditions. So where you're sat right now, that is typically what's it going to be. Depending on the time of the year, we just assume it's going to be 25 degrees. So 298 is 25 degrees Celsius. And you will learn this more in physics. But for now, just know that 298 is 25 degrees. And 100 kPa is 1 atmosphere. And that's the atmosphere as we live and breathe it. There are 3 standard enthalpy standard enthalpy changes that I'm going to cover. We do need to know these definitions off by heart, I'm afraid. The only way to do that is to write them out 15 to 20 times in a row. It really is. And understanding them can help with some of the reactions, but realistically, if I just show you the rules of how we use them, it'll make a lot more sense. Let's look at the first one, formation. I'm going to read the definition and I'll explain. The enthalpy change when 1 mole of a compound is formed from its elements in their standard states under standard conditions. So when I make something from the things that it's made out of that exist at room temperature. So let's look at this guy. So we've got here, we have ethanol. Ethanol, the alcohol. What we've got is, if I was to do the enthalpy of formation for this, what I'm saying is how much energy is released when I make this from the things that it's made out of. It's made out of carbon, which is coal at room temperature. It's made out of hydrogen, which is a gas. And it's made out of oxygen, which is also a gas. I've balanced it, and that is going to be the enthalpy of formation. If it's made from elements to form something, that's always going to be the enthalpy of formation. It can be other things as well, but that's going to be formation. And it is usually negative, it's usually exothermic. Standard enthalpy of combustion. So for combustion, we're burning a substance, and the definition that you need to know for this, and this is important, is the enthalpy change when 1 mole of a substance is completely burned in oxygen under standard conditions. So it's how much energy is released when I burn something completely. And when we say completely, we mean a plentiful supply of oxygen. If we don't have enough oxygen, that's going to be incomplete combustion. That's slightly different. And we'll look at that later on. But for the enthalpy change of combustion, how much energy is released when I burn ethanol? So ethanol's right there. Mix it with oxygen, and I'm going to form CO2 and H2O. When we combust anything, we're basically always going to form CO2 and H2O. So we're just going to have that there. And complete combustion produces CO2 and incomplete produces CO. So that's not relevant to this. But complete only accounts for CO2. And then we've got a more general one. So the general one, this ticks mostly every single box, but it's part of our spec. It's the standard enthalpy of reaction. So how much energy is released in this reaction. So if it's not a combustion, we're not burning it, and we're not forming it, we can basically say it's just an enthalpy of reaction. And this is the enthalpy change of reaction that occurs under molar quantities shown in the chemical equation with all reactants and products in their standard states under standard conditions. What that's just saying is, is everything here in this particular reaction, when they react under standard conditions, this is the energy released. So if I was to just do this at room temperature, room pressure, what energy is released? That's the standard enthalpy of reaction. There's a lot of words there, there's a lot of definitions there. Thankfully, we don't really have gap fills, but what I do have for you is a small task like this. What I'd like you to do is using these symbols here, this is combustion, this is formation, and this one is going to be reaction. Can you answer the following? Can you answer the following and label the following under standard conditions? Identify the enthalpy change as either combustion, formation, or reaction. So is it burning something? Is it being formed from elements? Or is it just like a standard reaction? And just so you can see what this is a capital delta, which is a triangle basically. This is a subscript C. This is a capital H. And then this is a theta. And that tells me it's standard conditions, but I'd prefer to have them there like that. So that would be enthalpy of combustion. This will be enthalpy of reaction, if it lets me do the R. And then this would be enthalpy of formation. And that's the way that we would do that grammatically speaking. Pause the video, have a go at those, and then I'm going to teach you about combustion. Okay. So I mentioned about the enthalpy of formation and the enthalpy of combustion. Now we need to be able to write those equations as well. So not only do you need to be able to identify them, but you also need to be able to write them out. I'll do one, and then you guys can do one. So we're going to write the equations to show the enthalpy of formation. Remember, formation is when a compound is formed, so a molar compound is formed, from its elements under standard states and conditions, which means if I want to do the formation of butane, it's formed from its elements. So the product is C4H10. That is going to be formed from its elements under standard states and conditions. So let's start off. The first element in there is going to be carbon. Let's do that in purple. Carbon at room temperature is a solid. Plus, we'll do hydrogen. Hydrogen, how it exists in a room temperature is a gas, and it's a diatomic gas. So it's H2 as a gas. Now, this equation isn't balanced. Thinking back to stoichiometry, we need to balance it. Best way to do that is by looking at the number of carbons you've got first of all. I've got 4 on the right-hand side over here, which means I need 4 over here. Big 4 there. Remember, 4, the big number tells me how many of those things I have. The small number tells me what's bonded to it. Hydrogen, H2. Over here, I've got 10 altogether, which means I need 10 on this side. This one comes in pairs, so I need 5 H2s. And that'll be that one balanced. I'd like to have a go at doing propanol. Next one we're going to look at is writing equations to show enthalpy of combustion. Now I'm going to teach combustion a little bit more later on, but there is a trick to doing combustion, and I'm going to call it CHO. And whenever you do combustion, you're just going to balance it using CHO. Let's write the equation first for butane. Remember, the enthalpy of combustion means I'm going to burn this thing. So butane, we're going to burn it. I'm going to write it here so I can have a bit more space. I've got C4, and I wrote 10 by accident. C4H10. And I'm going to react it completely in oxygen. So that is O2. Remember, O2, standard states and conditions, it exists as a gas and it's diatomic. Over here, the products. The products of complete combustion are going to be CO2 and H2O. Almost always. CO2 and just H2O. Now we need to balance it. And this is where it gets a bit tricky for you guys. With combustion, we have a rule where we can half the oxygen. We're allowed to use the oxygen in halves. It's a cool rule. It saves us some time. So let's go through this step by step. I said before, the technique I want you guys to use is CHO. So I just write CHO at the bottom. You can do this with me as well. By this, I mean, we're going to balance the carbons first. Carbons over here, I've got 4. Over here, I've got 1. I need 4 of these. Big 4 there. Carbons balance, tick. Next, we're going to do hydrogens. So CHO, hydrogens. I've got 10 over here, and then I've got 2 over here, which means I need 5 of these. Got 10 on both sides, I take that off. Oxygen, this is where it gets a bit tricky, so I'll do this in green. So for oxygen, you can see that this side has got all its big numbers, but this side doesn't. So we're going to work out this side first. Over here, I've got 5 lots of water, and each water has 1 oxygen, so 5 times 1 is 5. Over here, I've got carbon dioxide. And there's 2 of those in each carbon dioxide, and I've got 4 of them. 4 times 2 is 8. Little trick here, 5 add 8 is 13. Now, this is the trick that I want you guys to do that will always get you marks and is just correct. Where that O2 is, you're just going to write 13 divided by 2. That's it. Some of you might want to put 6.5 and do all these improper fractions, but 13 over 2 is mathematically correct. We just leave it like that. No calculations, no guessing, no rounding, no nothing. Just 13 divided by 2. Carbons, hydrogens, oxygens in that order. And you can see I've already got the answer to the first one. And you can see for the second one, we've got propanol. So this is going to be a little bit more tricky. I want to take you through this one as well. So I'll do butanol instead. So and you guys can have a go at doing propanol. So butanol is going to be C4H10, and I'm going to write it in the same way as you guys are familiar with it, is O. I'm going to combust it in oxygen, so that's O2 over here, just like that. And that is going to produce CO2 and H2O. So we need to make sure that we write CO2 and H2O. And then we're going to balance it in the order C, H, and then O. C, H, then O. We're going to start off with the carbons. I've got 4 on this side, which means I need 4 over here. Straight away done that. Hydrogens, I've got 10 over here, 2 over here. I'm just going to put a big 5 in front of that. You can see it's the same as before, and that's fine. Over here, oxygens. This is where things get a little bit weird because we've got an alcohol. So the rule before for CHO still works. Because we've got an alcohol, we've got one more thing to think about. So let's add these up. I've got 8 over here. I've got 5 over here. 5 add 8 is 13. Now, if I was to do 13 over 2 straight away, this would be wrong. 13 over 2 is 6.5, but then I've got this one here, that's 7.5. That no longer balances. That no longer works out. So we can't do that. To account for that oxygen in that alcohol, we're just going to subtract 1. So 13, because we've got an alcohol, we just subtract 1, and that gives us 12. Which means the final answer is just going to be this oxygen, she's 12 divided by 2. And yes, you can leave it like that. Or if you're really fancy with maths, you can just put a big 6 there. What I'd like you to do is to have a go at doing propanol using that same method. I'll leave my working out here so you don't forget. But for butane, it's just standard CHO. We don't need to subtract anything. And I'll see you guys in the next video.